When Neil deGrasse Tyson discovered the classified NASA documents that would force him to question everything he thought he knew about our planet's shape, he realized the scientific establishment had been hiding the most shocking truth in human history. The evidence wasn't just compelling, it was mathematically undeniable, and it came from the most advanced space missions humanity had ever conducted. But what Tyson found buried in those top-secret files would either destroy his career or revolutionize our understanding of reality itself. The crisis began on a routine Thursday morning in September 2023, when Tyson received an encrypted message from Dr. Marcus Webb, a former NASA engineer who had worked on the International Space Station for over 15 years. Webb claimed he had evidence that would shatter everything you believe about Earth's geometry, but he refused to discuss details over any digital communication. Tyson almost dismissed the message as another conspiracy theory from someone seeking attention. As director of the Hayden Planetarium and one of America's most visible advocates for scientific literacy, he received dozens of similar claims every month from people convinced they had discovered revolutionary truths that mainstream science was suppressing. But something about Webb's credentials made Tyson pause. This wasn't a basement researcher or internet theorist. This was a respected aerospace engineer with security clearance and decades of experience in actual space missions. Webb had personally conducted spacewalks, operated advanced instruments in orbit, and had direct access to data that most scientists could only dream of examining. Against his better judgment, Tyson agreed to meet Webb at a small café in Princeton, far from any location where they might be recognized or recorded. What he heard during that 3-hour conversation would haunt him for months and ultimately force him to confront the possibility that one of humanity's most fundamental assumptions about reality was completely wrong. Webb arrived carrying a briefcase filled with documents he claimed to have copied during his final weeks at NASA before his retirement. The papers contained technical specifications, orbital mechanics calculations, and photographic evidence from multiple space missions spanning 20 years. "Neil, I need you to understand something before we begin," Webb said, his hands trembling slightly as he opened the briefcase. "Everything I'm about to show you is classified at the highest levels. If this information becomes public, it will trigger the biggest scientific and philosophical crisis in human history." "Marcus, you're starting to sound like every conspiracy theorist I've ever encountered," Tyson replied. "What could possibly be so revolutionary that NASA would need to suppress it?" Webb pulled out a series of photographs taken from the International Space Station during different orbital passes. At first glance, they appeared to show the familiar curved horizon of Earth that every astronaut and satellite mission had documented for decades. But as Webb pointed out specific details in the images, Tyson began to notice something disturbing. "Look at the horizon curvature in these photos," Webb said, indicating a series of measurements overlaid on the images. "Now compare the mathematical predictions based on Earth's supposed spherical geometry with what we actually observe from orbit." Tyson examined the calculations with growing confusion. According to the standard model of Earth as a sphere with a radius of approximately 6,371 kilometers, observers at the ISS altitude of 408 kilometers should see a horizon with a specific curvature that could be calculated precisely using basic geometry. But the measurements from actual orbital photographs showed something impossible. The horizon curvature was consistently less than what spherical geometry predicted. The difference was small but measurable, and it appeared in photographs from dozens of different missions over multiple years. "This has to be an instrumentation error," Tyson insisted. "Camera lenses distort perspective, atmospheric refraction affects measurements. There are dozens of factors that could explain these discrepancies." Webb anticipated this objection and produced a second set of documents showing that NASA engineers had spent years trying to identify exactly those kinds of measurement errors. They had recalibrated instruments, corrected for atmospheric effects, used different camera systems, and even conducted specialized experiments designed to eliminate any possible sources of distortion. The conclusion was always the same: the horizon curvature observed from space was consistently less than what Earth's supposed spherical shape would produce. "Marcus, what exactly are you suggesting?" Tyson asked, though he was beginning to suspect he knew the answer. "I'm suggesting that Earth isn't a sphere," Webb replied quietly. "The evidence indicates we're living on some kind of disc-shaped structure that creates the illusion of spherical geometry when viewed from limited perspectives." Tyson felt his scientific worldview reeling. Everything about his education, his career, his understanding of physics seemed to argue against such a possibility. But the documentary evidence Webb was presenting appeared to be legitimate, and the mathematical discrepancies were undeniable. Webb continued with even more disturbing revelations. He showed Tyson internal NASA communications discussing what they called the geometry problem and efforts to suppress public discussion of orbital measurement discrepancies. There were memos instructing astronauts to avoid taking detailed horizon measurements during spacewalks and directives to process all Earth photography through computer systems that would normalize geometric anomalies. Most shocking were documents revealing that NASA had known about these measurement inconsistencies since the early Apollo missions. The agency had spent decades developing increasingly sophisticated explanations for why observed data didn't match spherical Earth predictions, but they had never seriously considered the possibility that their fundamental assumptions about Earth's shape might be wrong. "Neil, they're not suppressing this information out of malice," Webb explained. "They're terrified of what would happen to human civilization if people learned that our most basic understanding of our home planet is incorrect. The psychological, religious, and social consequences would be catastrophic." Tyson left the meeting with copies of Webb's documents and a promise to examine the evidence with complete objectivity, regardless of how uncomfortable the conclusions might be. For weeks he worked in secret, verifying calculations, checking data sources, and looking for any possible errors in Webb's analysis. The more he investigated, the more disturbed he became. The evidence for geometric anomalies was consistent across multiple space missions and observation platforms. Satellite data showed similar discrepancies when corrected for all known measurement errors. Even historical navigation records from ships and aircraft showed subtle inconsistencies with spherical Earth calculations. But the breakthrough came when Tyson realized that the flat Earth model Webb was suggesting wasn't the simplistic disk imagined by ancient civilizations or modern conspiracy theorists. The mathematical structure indicated something far more complex: a finite planar surface that somehow curved back on itself in ways that created the illusion of spherical geometry for most practical purposes. Using advanced topological mathematics, Tyson began modeling how such a structure might work. The surface could be curved in higher dimensions while remaining fundamentally flat in three-dimensional space, creating what mathematicians called a developable surface that appeared spherical from limited perspectives, but was actually planar when viewed comprehensively. This model explained all the observational anomalies Webb had documented. It predicted exactly the kinds of horizon curvature measurements that orbital missions had actually recorded. It accounted for why circumnavigation was possible while maintaining planar geometry. Most remarkably, it suggested that Earth's true structure was far more elegant and mathematically sophisticated than anyone had ever imagined. But accepting this model required abandoning centuries of scientific consensus and admitting that humanity's understanding of its home planet was fundamentally incorrect. Tyson struggled with the implications for months, unable to share his findings with colleagues who would dismiss them as pseudoscience without serious consideration. The ethical dilemma was agonizing. As a scientist committed to truth regardless of consequences, Tyson felt obligated to reveal his discoveries. But as someone who understood the social importance of scientific authority, he recognized that challenging such fundamental beliefs might undermine public trust in science itself. The decision became urgent when Webb contacted him with alarming news. NASA had discovered that classified documents were missing from secure facilities, and they were conducting internal investigations to identify the source of potential leaks. If Webb was caught with stolen materials, the information would be suppressed permanently and both men could face serious legal consequences. "Neil, we're running out of time," Webb said during another clandestine meeting. "If you're going to reveal this information, it has to be soon. Once they identify me as the leak, all evidence will disappear and this opportunity will be lost forever." Tyson made his decision based on a principle Carl Sagan had taught him decades earlier: extraordinary claims require extraordinary evidence, but when extraordinary evidence exists, it must be shared regardless of how extraordinary the claims appear. He began by publishing a carefully worded academic paper describing geometric anomalies in orbital observation data without explicitly stating conclusions about Earth's shape. The paper presented Webb's measurement data and mathematical analysis while inviting other researchers to examine the evidence and draw their own conclusions. The scientific community's response was initially skeptical but not dismissive. Several independent researchers began examining similar data from their own sources, and some confirmed the existence of measurement discrepancies that couldn't be explained by conventional spherical geometry. As more evidence accumulated, Tyson felt confident enough to present his complete analysis during a special lecture at the Hayden Planetarium. He titled the presentation "Reconsidering Planetary Geometry: Evidence for Complex Earth Structure," and invited the scientific community to engage with data that challenged fundamental assumptions. The lecture hall was packed with astronomers, physicists, and journalists who had heard rumors about Tyson's controversial research. For 2 hours, he methodically presented the orbital measurement evidence, the mathematical modeling, and the topological analysis that supported a planar Earth structure. The audience reaction was intense and polarized. Some scientists dismissed the evidence as misinterpretation or fraud. Others demanded access to the raw data for independent verification. A few acknowledged that the measurements were genuinely anomalous and deserved serious investigation. But the most significant response came from Dr. Elena Vasquez, a theoretical physicist who had been working on similar problems from a completely different direction. She approached Tyson after the lecture with evidence that quantum field theory predicted exactly the kind of geometric anomalies his orbital data had revealed. "Neil, I've been modeling vacuum structure at planetary scales," she explained. "The mathematics suggests that large gravitational bodies might exist in folded spacetime configurations that appear spherical locally but are actually planar when viewed from higher dimensional perspectives." Vasquez's theoretical work provided the missing piece of Tyson's puzzle, a quantum mechanical explanation for how Earth could maintain planar structure while exhibiting spherical properties. The planet wasn't simply a flat disk floating in space, it was a complex geometric manifold embedded in higher dimensional spacetime. Over the following months, more scientists began examining the evidence and contributing to what became known as Neo-Planar Earth theory. The model explained numerous anomalies in navigation, satellite mechanics, and gravitational measurements that had been dismissed as minor technical issues but actually represented signatures of Earth's true geometric structure. The public revelation came gradually as scientific consensus began shifting toward acceptance of the evidence. Tyson published a popular science book titled The Flat Earth Revelation: How Science Discovered Our Planet's True Shape, that explained the complex mathematics in accessible terms while addressing the social and philosophical implications of the discovery. Public reaction was intense but more positive than Tyson had expected. Rather than triggering civilization collapse, the revelation inspired renewed interest in advanced mathematics, theoretical physics, and space exploration. People were fascinated by the possibility that reality was far more complex and elegant than they had been taught. Religious groups struggled to incorporate the new understanding into traditional beliefs, but most eventually concluded that divine creation was even more remarkable if it involved higher dimensional geometric engineering. Educational systems began revising curricula to include the new planetary model while explaining how previous spherical approximations remained useful for most practical purposes. The discovery also inspired new technological developments. Understanding Earth's true geometric structure led to improvements in satellite navigation, gravitational wave detection, and space mission planning. The same mathematical principles that explained planar Earth structure were applied to understanding other planetary bodies and even galactic formations. Years later, when historians analyzed the period of transition from spherical to planar Earth models, they identified Tyson's courage in revealing controversial evidence as a crucial moment in scientific evolution. His willingness to challenge fundamental assumptions based on observational data demonstrated the self-correcting nature of scientific inquiry. Webb, who had risked his career to expose the suppressed evidence, was eventually vindicated when NASA officially acknowledged that their previous geometric models had been incomplete approximations. He received recognition as a whistleblower who had forced necessary scientific progress despite institutional resistance. The most profound impact of the flat Earth revelation wasn't technological or educational, it was philosophical. Humanity learned that even the most basic aspects of reality could be more complex than they appeared, that truth sometimes contradicted centuries of established belief, and that maintaining scientific humility was essential for continued discovery. Tyson often reflected on the irony that defending flat Earth theory had actually strengthened rather than weakened scientific authority. By demonstrating willingness to revise fundamental beliefs based on evidence, science had proven its commitment to truth over tradition. The universe had revealed itself to be stranger, more mathematically sophisticated, and more beautiful than anyone had imagined. And Earth, rather than being a simple sphere floating in space, turned out to be an elegant geometric structure that challenged human understanding while inspiring continued exploration of reality's deepest mysteries. Sometimes the most shocking truths hide in plain sight, waiting for someone brave enough to question what everyone assumes must be correct.